representing knowledge in AI. And the importance of knowledge is that even though there is a lot of data and machine learning based solutions, but they typically require very large models and a lot of data, a lot of training time. There are many situations where data is not available. Okay, for example, for any kind of security threat, detecting if the situation demands a security intervention, the data is typically not there. Okay, so in such cases, we'll have to make use of the problem knowledge, typically some kind of mathematical modeling, understanding the physics of the situation. Okay, and then introduce knowledge into an AI system. So predicate calculus has been a very important vehicle for representing knowledge in artificial intelligence. Now, what we covered last week was that we got deep into feed-forward network and backpropagation. There were important discussions on local minima. Backpropagation gets into local minimum because of the greedy nature of the algorithm. It keeps on minimizing error. Then momentum factor is used to accelerate the progress to the minimum. And symmetry breaking is essential because if you keep all the weights same and if the weights are same across the axis of symmetry, then the network doesn't converge to the correct values. Okay, so these were the important points associated with feed-forward network and backpropagation. Then we introduced a formal system and a very simple system called propositional calculus. So its formalization was introduced through these three axioms. A goes to B implies A, axiom A goes to B implies C, implies A implies B, implies A implies C, and A implies F implies F goes to A, implies A. So these three axioms and modus ponens rules is sufficient to capture propositional calculus. Now, if you start ab initio from axioms and only the inference rule, then proofs can become very complicated. Okay, they can take very long time and a lot of ingenuity. So there's a very nice theorem. It's called the deduction theorem. It is. It should be called a meta theorem because it is a statement about the property of the propositional calculus. It says that if you have been able to prove that A1, A2, A3 up to AN derives B, then you can assert that A1, A2, A3 up to AN minus 1 derives AN implies B. So this is a very, very convenient theorem, which we have stated without proof. We'll see if there is time to derive this proof. And this has been very useful in proving lots of theorems, which otherwise would have taken a long time and space. Now, the distinction between meta theorem and theorem is important. Theorem is a statement within the system. Meta theorem is a statement about the system. In AI, it is important to keep this distinction between about the system and inside the system. Now, for any formal system, soundness, completeness, and consistency are critical. Soundness refers to the fact that anything that is proved is indeed valid in the outside world. Okay, and completeness says that anything that is valid in the outside world should be provable in the syntactic world. Okay, so within the system, we should be able to prove anything that is valid. That refers to completeness. So completeness refers to the power of the formal system, and soundness refers to the correctness of the formal system. And consistency is such that the formal system should not be able to prove both P and not P. If you prove both P and not P, then F is proved. F is the false system. Okay. So if any system believes in P and not P, then it is called inconsistent. Though in real life, the intelligence systems have this inconsistent behavior all the time. Okay, and so these were the main points covered in the last week. If there is any question from anybody with respect to what was covered. Okay, then let's proceed. We introduced predicate calculus through a puzzle-like problem referring to Himalayan club problem. Now we would like to understand resolution in little more detail with some more insight into resolution. And resolution refutation goes this way. Suppose it is stated man X implies mortal X. This refers to the natural language sentence if all men are mortal. I have already proposed an interesting project for you in the lab. That project is from natural language sentences to predicate calculus formulae. The opposite is also an interesting problem. Given predicate calculus formulae, can you produce English sentences for this? Okay, an interesting possibility is that predicate calculus formulae converted to English language sentences and then using them for prompting a large language model like DeepSeek or ChatGPT or any large language model. Okay, it is as if a predicate calculus based knowledge representation is now interacting with a large language model via the intermediate step of English. Now, those of you who have been using ChatGPT, if you have tried to do any more complicated problem on these kind of large language models, you have seen that you need to give the English language instructions very carefully. So it is almost like programming a machine in English language. Okay, so there you need to have a grip on the problem you're solving, and also you need to understand the properties of English language. Okay, that is why it is no wonder why all these top industries like Google, Facebook, IBM, Microsoft, okay, why they have so many people coming from humanities and social sciences who give insight into social language phenomena, social science phenomena, psychological phenomena. AI is extensively being used for solving mental problems, health problems, social phenomena. For example, whole Facebook's idea of connecting the whole world through the social network is based on human behavior and psychology. Okay, what is the meaning of friendship? What is the meaning of closeness? What is the meaning of belonging to a group? Okay, so these kind of deep insight into how human beings perform is crucial for artificial intelligence. So that's why in this particular course, you need to broaden your perspective with respect to what AI is. AI is not only machine learning. I'm saying this again and again. Machine learning happens to be a technique for solving AI problems. And without a clear understanding of what the problem is and insight into these problems, the course course will not be a success. Okay, so my purpose is to give you that perspective as to how to solve problems that human beings are good at. Okay, and therefore only algorithm, only maths, only modeling is only a small part of AI. You need to broaden your perspective that way. Okay, so take a broad view of the course, understand that philosophy, humanities, physics, mathematics, coding, algorithm, everything is necessary for this course. Okay, otherwise you will not enjoy and relate to the course. Okay, so now resolution refutation is proof by contradiction. So this statement is man X implies mortal X, which says all men are mortal. And then we have to prove, given the fact that Shakespeare is a man, Shakespeare is mortal. So this is proof by contradiction. Now here, the clauses are not man X or mortal X. Okay, so this Shakespeare should be X. It is asserted that Shakespeare is a man. We have to prove Shakespeare is mortal. So we first negate the goal, Shakespeare is not a man. And let's see the consequence of saying this, that Shakespeare is not a man. So then we do instantiation of the variable. We have already negated the goal, not mortal Shakespeare. And we have not man Shakespeare or mortal Shakespeare, where X has been instantiated with Shakespeare. Now, not mortal Shakespeare and mortal Shakespeare, they resolve and get not man Shakespeare. But Shakespeare is already asserted as man, so this should be man Shakespeare. Okay, so we are making use of all the rules and facts given to us. This is the rule: all men are mortal. This is the fact: Shakespeare is not mortal. And then through resolution, we have got a contradiction. Contradiction is indicated by the null clause. That's how the algorithm stops. So resolution tree consists of this kind of subtrees where we have the resolvent 1 and resolvent 2 giving rise to the resolute. Okay, so if we have not mortal Shakespeare and not man X or mortal X giving rise to not man Shakespeare, then not man Shakespeare is the resolute. This is resolvent 1 and this is resolvent 2. Now, when we do resolution, it implicitly means that there is a search involved. Which are the two clauses which we should use for resolution? Okay, so given many clauses, which two should we choose? So there are a few heuristics for resolution search. The first is called goal support strategy. You always start with the negated goal, okay, and look for a clause with which this negated goal will resolve and produce a resolute. And the other heuristic is called the setup support strategy. Always one of the resolvents is the most recently produced resolute. Okay, so by resolution, a resolute comes out, and that is the new resolvent for the next step of the resolution. So these are heuristics for resolution search. Otherwise, resolution search can become extremely complicated and it can also get into a dead end. Okay, for very large problems, resolution has to be made efficient. Now, Prolog, which you learn in the class, has optimized its internal strategy for searching for resolvents, and that's a very efficient system. So all of you will have to use what is called SWI Prolog, SWI Prolog. It will be downloaded in the lab. Okay, and the other option is GNU Prolog. They have slightly different flavor. So SWI Prolog is quite popular. This will be downloaded in the desktops in the lab, and your assignment will be based on SWI Prolog. Now, inferencing in predicate calculus happens in 3 ways: forward chaining. Given P and P implies Q, infer Q. So this is called forward chaining. You match P with the left-hand side of P implies Q and right Q. So this is how forward chaining occurs. In backward chaining, you match the right-hand side and then assert the left-hand side. Okay, so check if P exists. And if P exists, then this forward chaining has succeeded. Resolution refutation is proof by contradiction. So here you negate the goal and convert all pieces of knowledge into clausal form. These are disjunction of literals. See if the contradiction is indicated by null clause. The null clause is the termination condition. It has to appear as the process of resolution. Now, what if you do not get a null clause, whatever you do? Okay, you have carried out all possible searches with all possible pairs of clauses. If the null clause doesn't appear, it means that you are not able to prove a contradiction in the system. So this means that the clause that you want to prove, given the facts and rules, cannot be proved from the given facts and rules. Okay, what you want to prove is not provable. So this is an indication for resolution refutation failing by failing to prove the clause. Okay. Forward chaining, backward chaining are also extensively used in AI systems, extensively. Forward chaining and backward chaining, which process to use, okay, depends on the what is called the fan out and fan in factor of the knowledge base. Okay, how many rules have the right hand side same, even though the left hand side changes? So, for example, in disease diagnosis systems, many times, okay, all the case symptoms are same, but the disease is different. Okay, so suppose you have sneezing and fever. Sneezing and fever can be symptoms for many different diseases. You need more, more evidences, more facts, more tests. So, so how many different left-hand sides give rise to, how many same left-hand sides give rise to different right-hand sides? Similarly, how many different right-hand sides are indicated by um, uh, by different left-hand sides? Okay, this is called the fan in and fan out factor of the rules. So that determines whether you should use forward chaining or backward chaining. It is decided by the problem property also. Okay, so there are two kinds of problems in AI: analysis problem and synthesis problem. If you want to diagnose something, let's say disease is to be diagnosed, or a loan application has to be sanctioned, visa application has to be sanctioned, then which chaining should I use, forward chaining or backward chaining? And if we have to assemble something, it is a generative AI problem. If you have to generate something, then should it be forward chaining or backward chaining? Okay, these are the guiding factors. Think about them and also read them up. So, some interesting questions can arise as to the appropriateness of forward chaining and backward chaining. Now, in the basics of inferencing is modus ponens, right? Given P and P implies Q, you infer Q, but you start with the negation of Q. You start with not Q, and then arrive at a contradiction. So modus ponens, the resolution tree corresponding to modus ponens is this. Not Q is already asserted. This is Q was the goal, so not Q is the negated goal. You want to show contradiction. So not Q is taken, and then not P or Q is P implies Q. Then from not Q and not P implies Q, you obtain not P. And P is asserted, so not P and P gives rise to null clause. So this is the resolution tree corresponding to modus ponens. Similarly, it is instructive for you to think about the resolution tree of something called modus tollens rule. Okay, there is also a rule called modus tollens. Modus tollens is given P implies Q and not Q, you can imply not P. That's called modus tollens. Okay, so create the resolution tree for modus tollens to convince yourself that resolution is consistent with modus tollens rule also. Now, what is the theoretical basis of resolution? Okay, why does resolution work? And it is based on what principle? The principle is the following. Resolvent 1 and resolvent 2. Resolvent 1 and resolvent 2 implies resolute. So that is a tautology. Okay, so that's a tautology. You can take resolvent 1 and resolvent 2 implies resolute 2. You can resolute. You can take this whole formula, draw the truth table, and if resolvent 1 and resolvent 2 indeed implies resolute, then this truth table will come out to be true in all the rows in the final column. So it will be a tautology. So you see P or Q and not P or Q give rise to Q as a resolute. Indeed, P or Q and not P or Q implies Q is a tautology. Okay, so this you can do by predicate calculus algebra or by drawing a truth table. And there is a third method for doing this. The third method is called semantic tree, which is a very interesting algorithm. Okay, it goes as follows. So I want to prove that P or Q and not P or Q implies Q. Okay, so what I start with, this algorithm is called a semantic tree based algorithm. I start with not Q because this is what needs to be contradicted. The uh, not Q should give rise to contradiction. Okay, P implies Q and not P, P or Q and not P or Q should give rise to Q. And we would like to prove this by contradiction. So take not Q and also take P or Q and not P or Q together. Now, how can P or Q and not P or Q be true? It is an AND formula. AND formula is true only if both its components are true. So then I write P or Q and not P or Q. Okay, this is called a semantic tree. Now, not P or Q, how can it be true? It can be true either by not P being true or Q being true. Okay, then not P is here. And P or Q needs to be processed now. Now P or Q can be true either by P being true or Q being true. So you write the children as P and Q. Now what will happen is that take any path from leaf to the tree, take any leaf and traverse the path from the leaf to the root. Okay, and you will meet contradiction on the way. So let's start from here. I got P here and then not P. So contradiction. I start with Q here. I go to the parent, go to the parent, go to the parent, not Q, contradiction. I start from Q here, go to the parent, not Q, contradiction. So all paths in this semantic tree give rise to a contradiction. So this means that not Q is not provable from P or Q and not P or Q. So this is a very elegant method of showing contradiction or proving a tautology, which is in the form of an implication. Just take the right-hand side of the implication, negate it, and write the left-hand side below the negated right-hand side. Okay, and then keep on decomposing the formula, and every path should lead to a contradiction. This is how semantic tree operates. So which are the 3-4 methods of proving a tautology? One is by truth table. Okay, second is by semantic tree. The third is by going into the formal system and showing that the tautology is a theorem in the formal system. So there are many ways of doing this. Or you take the expression and apply deduction theorem, okay, and then prove it. So make sure that you are proficient in making use of deduction theorem. That's a very powerful decision procedure. So some of the theoretical bases of resolution are the following. Resolution leads to what is called monotone inference. The size of the knowledge base goes on increasing as we proceed with the resolution process, since intermediate resolvents are added to the knowledge base. So what we prove is indeed true, and it becomes part of the knowledge base. So the knowledge base keeps on increasing. Non-monotone inference is something where the size of the knowledge base does not increase. Okay, human beings use non-monotonic reasoning. We assume some hypothesis, then see the consequence of the hypothesis. If the consequence does not match up to reality, we withdraw the consequence and revise the hypothesis. So suppose a doctor is diagnosing based on the symptoms. The doctor says that I think the disease is jaundice, okay, and prescribes medication, etc. for this. But over time, it turns out that the symptoms don't go, and therefore there is a contradiction in the observations, and then the hypothesis needs to be revised. Okay, in real life, this always happens. Okay? And in particular, if you talk to medical practitioners, And the field of medical AI is extremely important these days. It is a heavy consumer of AI techniques. Talk to some doctors. If you have some doctors in the family or friends are doctors studying medicine, talk to them. It will be interesting for you to see what kind of inferencing do they use. Do they use forward chaining or backward chaining, or do they use resolution refutation? Most of the times, the doctors start with a hypothesis in mind. Okay, the symptoms indicate that this is the disease. And good doctors are ones who very quickly home onto the correct diagnosis. Okay, the correct underlying problem is diagnosed very quickly by good doctors. They don't have to specify an umpteen number of tests. So in the initial phases of medical profession, the doctors with less experience suggest all kinds of tests. Many of the tests are not really useful. As the doctors advance in their experience, their search for the correct hypothesis gets reduced. Okay. So non-monotonic reasoning is the real life reasoning. Resolution refutation is an approximation. So now to show that the knowledge base keeps on growing, let's go back to the resolution tree for our problem. You remember this problem that ABC are members of the Himalayan club, and every member in the club is either a mountain climber or a skier or both. A likes whatever B dislikes and dislikes whatever B likes. A likes rain and snow. No mountain climber likes rain. Every skier likes snow. Is there a member who is a mountain climber and not a skier? So we would like to apply resolution refutation to solve this problem. To be able to apply resolution refutation, our first task is to convert natural language sentences into clauses. So this is an elaborate procedure, and we have to identify the facts and rules very carefully. This is what is AI with respect to predicate calculus. So A is a member, member A, B is a member, member B, member C. Every member is a mountain climber or skier, becomes a for all x formula. So for all x is called universal quantification. X is the variable. So for all x, member x implies mountain climber x or skier x. For all x, mountain climber x implies not like x rain. No mountain climber likes rain. For all x, skier x implies like x snow. All skiers like snow. For all x, like bx implies not like ax. If B likes something, A does not like it. And if B dislikes something, A likes it. Like A rain, A likes rain. Like A snow. Now the question is, there exists X. This is existential quantifier. Member X or mountain climber X and not SKX. Is there an X who is a member of the club and is a mountain climber but not a skier? Okay, this needs to be proved from the knowledge base given. Since resolution refutation is by contradiction, we have to contradict the goal. But before that, there is little more work. We have to convert all universally quantified expressions with implication into clausal form. So for all x, member x implies MCX or SKX gets converted to not member x or MCX or SKX. For all x, skier x implies LKX no is not SKX or LKX no, and so on. Okay, all implications are converted into the clausal forms. So here we have converted into clausal forms. The important step of contradicting the goal comes here. There exists x, member x, and mountain climber x, and not skier x is converted to negation. So when you negate an existential quantifier, the existential quantifier becomes universal quantifier, and everything inside the universally quantified expression gets negated. So there exists X member X and MCX and not SKX becomes for all X, not member X or not MCX or SKX. So this is the new clause which is added to the knowledge base. And then we have to standardize the variables. So member A, member B, member C, these are called grounded clauses. There is no variable here. All the arguments are constants. And the clause with the implication introduces its own variable, not member X1 or MCX1 or SKX1. Then all skiers like snow, X2, no mountain climbers like rain, X3. If if A likes something, B doesn't like it, X4. If B does not like something, A likes it, X5. Likes A rain, likes A snow. And is there a member who is a mountain climber and not a skier? X6. We are interested to find the value of X6, okay, by instantiation. So instantiating a variable with a constant is called unification. So now when these clauses are put together, we should be able to find a contradiction. These clauses do not hold together. They lead to a contradiction. So this is how the resolution proceeds. We start with the goal clause as one of the resolvent. No, not the goal clause, sorry. If A does not like something, then B likes it, and A likes snow. So from these two resolvents, we get the resolute B does not like snow. So this is what is meant by monotonicity of the knowledge base. You see that B does not like snow is added to the knowledge base, and it is true. Okay, we don't have to retract it. It is true. Then B does not like snow, and all skiers like snow. These are the two resolvents giving rise to the resolute B is not a skier. The fact that B is not a skier is added to the knowledge base. Now the size of the knowledge base has grown from X to X plus 1, now X plus 2. Now this is resolved with all club members are either a mountain climber or a skier. From there, we have been able to prove that if B is not a member, then if B is a member, then B must be a mountain climber. So this way, we keep on generating new clauses which get added to the knowledge base. Okay, so this is what is meant by saying that resolution refutation is monotonic. Okay, whatever you prove gets added to the knowledge base and participates in further inferencing. So now these are the well-known examples of predicate calculus. Man is mortal, Shakespeare is a man, Shakespeare is mortal. These are 2000-year-old examples coming from Greek tradition of logic. So the origin of predicate calculus is language, okay, because we have to represent the knowledge contained in sentences, and that comes from the basic structure of the sentences, the subject and the predicate. Grass is green is the predicate, grass is the subject. Okay, so predicate is a function which maps from a domain D to the range T, F, true and false. Okay, so predicates are functions whose outputs are true and false. So predicate calculus cannot deal with a large class of sentences which are interrogative and exclamatory. Then all kinds of sentences can be represented using predicate calculus, provided you know which operator to use and which quantifiers to use. Predicate calculus is also a very succinct knowledge representation for sentences. All even numbers are divisible by 2. If you have to represent it in propositional calculus, you have to take infinite number of propositions because there are infinite number of even numbers. But in predicate calculus, you can represent this by a very, very concise expression. Then predicate calculus is surely finer than propositional calculus. If we say grass is green, ball is green, leaf is green, the greenness is a common property. So we need a knowledge representation scheme where this commonness is captured. It is not possible in propositional calculus. In predicate calculus, this can happen. Then we can have n place predicates where n can take any value. But when we convert language to predicate calculus expressions, we don't see typically more than 4 arguments. Okay, x gives y to z, give x, y, z. X gives y to z through w, then give x, y, z, w. And this is also universal, as I pointed out. In Hindi also, the same knowledge representation will apply. Now we get into the theoretical foundations of predicate calculus-based inferencing. The primitive, the most important building block of predicate calculus is n-ary predicate, a predicate which takes n arguments. So P, A1, A2 up to n is a predicate which operates on d to the power n, okay, d cross d up to n, and goes to a tree 2 and false. This is the formalization of the predicate. And the arguments of the predicates can be variables and constants. There is no restriction on that. When for a predicate, all arguments are constants, this is called an fully instantiated predicate or grounded predicate. Predicate, all whose arguments are constants. We typically mix predicates with functions. So there can be n-ary functions. Let's say f goes from d to the power n to d. Then we are mapping an n tuple to a single tuple. For example, President of India is Draupadi Murmu. So here President is a one-place predicate. The argument is India. And the result of applying this predicate is Draupadi Murmu. Now President, the argument can change here to USA, and then the output will be Trump. Okay, so this is how the predicate operates. Now predicates are higher order functions. The constants and variables are called zero order objects. Predicates and functions are called first order objects. Okay, because they operate on zero order objects and give rise to zero order objects again. So that's why they are called first order objects. Prime Minister of Fiji is older than the President of Fiji. So older is a predicate. Prime Minister is a function which operates on Fiji and returns the Prime Minister of Fiji. President is a function, operates on Fiji and returns the President of Fiji. So, and this older predicate is asserting that the Prime Minister of Fiji is older than the President of Fiji. The operators we know are and, or, not, exclusive or, universal quantification, implication, and there exists. We also know that all these operators are not needed. There is a minimal set of operators. Okay, so you can operate with, for example, not, implication, and one of the quantifiers, existential or universal. Universal quantifier, existential quantifier, all men are mortal. For all x, men x implies mortal x. Some men are rich, there exists x, man x, and rich x. Do also think about why for all always takes implication as the operator, whereas there exists always takes and as an operator. Okay, so this is something you should think about as to why implication and universal quantification go together, and there exists go together. Could you have there exists x, man x implies rich x? Or could you have for all x, man x and mortal x? Okay, think about these questions. Now, in predicate calculus also, we have tautologies. So some of the very well-known tautologies are not for all x, px, not for all x, px implies there exists x, not px. And not there exists x, px implies for all x, not px. So take the second tautology in English. Not a single man in the village is educated implies all men in this village are uneducated. Okay. So tautologies are important instruments in logic, but they are very uninteresting statements as far as language is concerned. Tautologies are very uninteresting. Okay, in the sense that what are you saying here? Not a single man in the village is educated implies all men in the village are uneducated. This implies part is not bringing in any additional information. Okay, so tautologies are structures which are guardrails. Okay, these are guardrails against wrong inferencing. These are instruments of logic, but these are not interesting with respect to actual real life knowledge and application. So when we use predicate calculus and do inferencing, the forward chaining goes as follows. Suppose it is given all men are mortal and man Shakespeare. Then we match man Shakespeare with man X. In this process, X gets instantiated to Shakespeare, and the right-hand side is rewritten as mortal Shakespeare. So we find the conclusion in one step. In backward chaining, we are required to prove Shakespeare is mortal. That is our goal. So we take the goal mortal Shakespeare and match it with the right-hand side of the given rule. Man X implies mortal X. Now X gets instantiated to Shakespeare. We carry the instantiation to the left-hand side. We get man Shakespeare. And indeed, in the knowledge base, man Shakespeare is asserted already. Okay. And therefore, this goal has been proved. Forward chaining and backward chaining. In forward chaining, we start from facts, go to the goal. In backward chaining, we start from the goal and arrive at the facts. Now, one of the important fields of AI is question answering. Question answering is very crucially dependent on predicate calculus. There are what are called WH questions and the corresponding knowledge to answer those WH questions. What are the WH questions? What, where, who, when, which, how, and why. Okay, so these are basics of any question answering system. Not in terms of automation, but in any question answer, these are the WH questions. Out of these, what, where, who, when, which, these are called factoid questions. Their answer is typically a single phrase or sentence or entity. Okay. What is the capital of India? Delhi. Okay. Where is Calcutta located? West Bengal. Who is the president of India? Draupadi Murmu. When did India get independence? 1947. Which is the largest state in India? Rajasthan. Okay, so these are called factoid questions. These questions are much, much simpler compared to the last two questions, how and why. How is a procedural question. How do we travel from Mumbai to Delhi? And you have to give a step-by-step procedure. How do I make dosa? Okay, a step-by-step procedure for this. Why? Why? Why is there why is there sadness in the world? A very complex question. Okay, so why is a reasoning question? How is a procedural question? And other questions are called factoid or declarative questions. This is so fundamental to any kind of question answering and any kind of AI system, conversational AI, chatbots, for example, that we need to be very clear about these WH questions and their categories. We know that today's large language models are extremely good at answering all these questions, including how and why. Okay, and if you have heard of jailbreaking, that means can you ask a harmful question to a large language model? Okay, how do I do bank robbery? So large language models will not answer this question. But you can ask indirect questions, and you can find a chink in the armor for large language models and make it answer this question. So this how is a procedural question, and today's large language models in guarding against jailbreak needs to understand these how questions very carefully. Okay? And why questions are much more complex, because they require reasoning. When you do why, we have to do inferencing. Okay, so in the background, resolution, refutation, forward chaining, backward chaining, these are involved. But these are our large language models these days are extremely good in answering these questions. And factoid questions are child's play. But the main problem is also to make them multilingual, okay, for which you need training data from various languages. So any question on WH questions? So some of you might think of doing a project in answering WH questions, especially why and how questions. Okay, I guess I'll